welcome to this problem walkthrough on the sliding window median. In this session, we'll dive into how to solve this interesting problem that involves calculating medians over a sliding window of numbers. It's a great opportunity to explore concepts like sorting, data structures, and optimization. Let's get started. The sliding window median problem involves finding the median of a dynamic subset of elements within a given array. Imagine you have an array of integers and a window of size k that moves one step at a time from the start of the array to the end. For each window position, your task is to calculate the median of the numbers inside that window. Now, the median is defined differently based on the number of elements. If the list has an odd number of elements, the median is the middle value when sorted. If the list has an even number of elements, the median is the average of the two middle numbers when sorted. The input to the problem includes an integer array nums, where each value can range between -10,000 and 10,000, and an integer k representing the window size. The output is an array of floating point numbers, each representing the median for a specific window. These medians need to be precise, without any truncation. This problem also requires that your solution be efficient, making it crucial to consider the constraints on input size and the computational limits imposed by large arrays and window sizes. Looking at a concrete example, suppose nums is 1, 3, -1, -3, 5, 3, 6, 7, and k is 3. The output array for this input is 1.0, -1.0, -1.0, 3.0, 5.0, 6.0. Let's break it down step by step. When the window is 1, 3, -1, the sorted order is -1, 1, 3, and the median is the middle value, 1.0. When the window moves to 3, -1, -3, the sorted order becomes -3, -1, 3, and the median is -1.0. Similarly, for the next window, -1, -3, 5, the sorted order is -3, -1, 5, and the median remains -1.0. As the window slides further, we compute the medians for -3, 5, 3, 5, 3, 6, and 3, 6, 7 as 3.0, 5.0, and 6.0, respectively. This example illustrates how the median changes as the window slides over the array. Here's another example to solidify the concept. If nums is 1, 4, 2, 3, and k is 2, the output array is 2.5, 3.0, 2.5. For the first window, 1, 4, the sorted order is 1, 4, and since there are two elements, the median is the average of the middle two numbers, which is 2.5. For the next window, 4, 2, the sorted order becomes 2, 4, and the median is 3.0. Finally, for the window 2, 3, the sorted order is 2, 3, and the median is 2.5 again. This example highlights how the median calculation works for windows where k is even. It's also worth noting that the problem constraints require an efficient solution, as the length of nums can be up to 100,000, and the algorithm must perform well even with large inputs. The problem also involves handling certain edge cases. For example, if the input array has only one element, such as nums equals 5 and k equals 1, the output is simply 5.0, as the single element is the median. If all elements in the array are identical, like nums equals 2, 2, 2, 2, with k equals 2, the median for every window remains 2.0. Another edge case occurs when the window size equals the length of the array. For instance, if nums equals 7, 3, 5, and k equals 3, the entire array is the only window, and the median is 5.0 after sorting 3, 5, 7. These examples emphasize the need to handle varying input scenarios while maintaining precise floating point calculations for the medians. Finally, let's consider a slightly larger edge case. If nums is 1, 2, 3, 4, 5, and k is 5, the window encompasses the entire array. Sorting 1, 2, 3, 4, 5 gives us the median is 3.0, which is the middle value. Since the window size matches the array length, there's only one median to compute, and the output is simply 3.0. This example highlights the simplicity of the calculation when k equals the array length. Overall, this problem challenges us to design an efficient algorithm that handles both large inputs and precise floating point operations, ensuring correctness across diverse scenarios and edge cases. To start solving the sliding window median problem, we could consider a brute force approach. The idea here is simple. For every window position, extract the k elements within that window, sort those elements, and then calculate the median. If the window size k is odd, the median would be the middle element in the sorted list. If k is even, it would be the average of the two middle elements. While this approach is straightforward to implement, its complexity makes it impractical for larger inputs. Sorting the k elements for each window takes k log, k time, and within k plus 1 total windows, the overall complexity becomes n k log k. In the worst case, where k is close to n, this results in n squared log n, which is computationally expensive for larger arrays. Hence, while intuitive, this method is not suitable for scenarios requiring high efficiency. To address the inefficiency of the brute force approach, we can use an optimized solution based on the two heaps method. In this strategy, we maintain two heaps, a max heap to store the smaller half of the window's elements and a min heap for the larger half. The key is to keep the heaps balanced, ensuring that their size difference is at most 1. This balance allows us to efficiently derive the median. If the window size is odd, the median is simply the top of the heap with more elements. If the window size is even, we take the average of the tops of both heaps. As the window slides, we dynamically add the new element to one of the heaps and remove the element that is no longer in the window. Rebalancing the heaps, which involves removing and inserting elements, is efficient due to the logarithmic time complexity of heap operations. This method significantly reduces the overall complexity to n log k, making it much more suitable for large inputs. Another optimized approach involves using a balanced binary search tree, or a sorted list in Python, to maintain the elements of the current window in sorted order. With this method, we can insert and delete elements efficiently while preserving the order. The median can then be quickly accessed by indexing the middle element or elements, depending on whether the window size is odd or even. Operations like insertion and deletion in a balanced BST take log k time, and accessing the median is 1. When sliding the window across the array, this approach achieves an overall time complexity of n log k, which is comparable to the heap-based method. However, implementing and maintaining a balanced BST often requires more effort and careful handling, especially in programming languages without built-in support for such structures. Among the different strategies, the heap-based approach stands out as the most practical choice. Heaps are particularly well suited for maintaining dynamic sets of the smallest or largest elements, which is exactly what this problem requires. The inherent structure of heaps allows for straightforward and efficient rebalancing, making them easier to implement and debug, especially in Python, where the heap module provides robust support for heap operations. The aha moment in this problem is realizing that dynamically maintaining the median maps naturally to the two-heap structure. By balancing the heaps, we ensure the median can always be derived in constant time. Comparing the options, the brute force approach, while simple to implement, is computationally expensive. The BST-based approach is efficient but more complex to implement, and the heap-based approach strikes the best balance between runtime efficiency and ease of implementation. Taking all these factors into account, the heap-based approach emerges as the optimal solution for the sliding window median problem. It offers an excellent combination of efficiency, simplicity, and clarity, making it highly effective for this task. The two-heap strategy not only reduces the computational overhead but also ensures the solution is straightforward to implement and maintain, even for larger inputs. This balance of practicality and performance is why the heap-based method is the preferred choice for this problem. The sliding window median problem focuses on determining the median of every contiguous subarray, or window, of size k as it moves across the array nums. The median is defined as the middle element of the sorted window for an odd-sized window, or the average of the two middle elements for an even-sized window. To solve this problem using a brute force approach, we begin by understanding the input, the integer array nums and the window size k. It's important to confirm that k is within bounds, meaning it must be at least 1 and no larger than the length of nums. Once initialized, we slide the window across the array. For each starting index, a subarray of size k is extracted using slicing, such as nums, I plus k. After extracting the window, we sort its elements in ascending order. Sorting is necessary to identify the middle element or elements, and Python's timsort algorithm can handle this efficiently for small windows with a time complexity of k log k. After sorting the current window, the next step is to find its median. For a window of odd size, the median is the middle element, located at index k//2 of the sorted window. For an even-sized window, the median is calculated as the average of the two middle elements, specifically window k//21 and window k//2. Once the median is computed, it's appended to a results list called medians. This process is repeated by sliding the window one position to the right, incrementing the starting index, and recalculating the median for the new window. When the window reaches the end of the array, the algorithm outputs the collected medians. A few edge cases are worth noting. If k equals 1, each median is simply the corresponding element of nums. If all elements in nums are identical, the median is the same value for every window, and when k is close to the size of nums, only a few windows need to be processed. These considerations help ensure the algorithm handles all scenarios correctly. Sorting each window is straightforward but computationally expensive, which highlights the key challenge of the brute force approach. Sorting allows easy access to the middle elements needed for median calculation, but it becomes a significant overhead as the window slides because the sorting process repeats for every new window. Consequently, the brute force method has a time complexity of O n k plus 1 *k log k, where n is the length of the array. This complexity arises from processing n k plus 1 windows, each requiring O k log k time for sorting. For large arrays or windows, this inefficiency is a major drawback. To improve performance, advanced techniques utilize optimized data structures. Balanced heaps, such as a max heap and min heap, are a common choice for dynamic tracking of the smallest and largest elements in the window, enabling efficient median computation. Alternatively, self-balancing binary search trees, like Java's treeset, can be employed to maintain a sorted state of the window with efficient insertions and deletions. These structures form the basis of optimized solutions. To implement an optimized solution using heaps, we start by initializing two heaps, a max heap for the smaller half of the elements in the window and a min heap for the larger half. The heaps are balanced so that the max heap contains either the same number of elements as the min heap or one more element if the window size k is odd. For each new element added to the window, we insert it into the appropriate heap while maintaining the heap properties. If the heaps become unbalanced, we rebalance them by transferring elements between the heaps. As the window slides, we need to remove the element that is no longer part of the window. This requires identifying which heap contains the outgoing element and removing it accordingly. Once the heaps are updated, the median can be computed efficiently. If the window size is odd, the median is the root of the max heap. If it's even, the median is the average of the roots of the max heap and min heap. This approach ensures that each step is performed in logarithmic time relative to the window size. Finally, after computing the median for the current window, it is appended to the results list, which will ultimately contain the medians for all windows. The optimized approach significantly reduces the time complexity compared to the brute force method. Instead of O n k plus 1 *k log k, the optimized solution achieves a time complexity of O n log k. This improvement comes from the fact that each insertion or deletion operation in a heap takes O log k, and these operations are performed n times in total as the window slides across the array. To illustrate, consider the array nums equals 1, 3, minus 1, minus 3, 5, 3, 6, 7, with k equals 3. For the first window, 1, 3, minus 1, the median is 1. For the second window, 3, minus 1, minus 3, the median is minus 1, and so on. The result is the list 1, minus 1, minus 1, 3, 5, 6. This optimized approach balances efficiency and correctness, making it well suited for handling large datasets. Here, we start by importing the bisect module, which helps us efficiently manage the sorted sliding window. The solution class defines the method median sliding window, which takes two inputs, nums, the list of numbers, and k, the size of the sliding window. Within this method, we define a helper function called getMedian. This function calculates the median for a given sorted window. If the size of the window is even, it calculates the average of the two middle elements. If the size is odd, it simply returns the middle element. Next, we initialize the sliding window by taking the first k elements from nums and sorting them. The median of this initial window is computed using getMedian and stored in the medians list. Then, we start iterating through the rest of the nums array, beginning at index k. For each iteration, we first remove the element that is no longer in the window. This is done by finding its position in the sorted window using bisect_left and then deleting it. After that, we add the new element from nums to the window using insort_left, which maintains the sorted order. Finally, we calculate the median for the updated window and append it to the medians list. At the end of the function, we simply return the medians list, which contains the median values for each sliding window as it moves through the array. This approach ensures that we efficiently maintain and update the sorted order of the window, allowing us to calculate the median in logarithmic time for each step. The overall complexity of the solution is manageable, making it suitable for moderately large input sizes. Here, we begin implementing the solution by defining a helper method called getMedian that calculates the median of a sorted list. The method first determines the middle index of the list. If the size of the list is even, the median is the average of the two middle elements. Otherwise, for an odd-sized list, the median is simply the middle element. Next, the median sliding window method is defined. This method takes an integer array nums and the window size k as inputs, and it returns an array of medians for each sliding window. To start, we declare a list called window to represent the current sliding window and a double array medians to store the calculated medians. The first loop iterates over the initial k elements of the input array, adding them to the window list. Afterward, the window is sorted, and its median is calculated using the getMedian helper method. The median of this first window is stored in the first position of the medians array. Following the initialization of the first window, we continue by sliding the window across the array. This involves iterating through the rest of the elements in nums, starting from index k. For each new position, the element that falls out of the window is removed from the window list. This is done using collections.binary search to locate the index of the element to remove. Next, the new element entering the window is added in the correct sorted position. Again, collections.binary search is used to determine the insertion point, and if the element isn't found, the insertion point is adjusted to maintain the sorted order. Once the window is updated, the getMedian method is called to compute the median of the current window, and this value is stored in the corresponding position of the medians array. Finally, after processing all sliding windows, the method returns the medians array containing the median values for each window. To solve the problem, we start with a simple example where the window size, k, is odd. Given the input array nums in k equal to 3, we begin by initializing a window with the first three elements, 1, 3, -1. After sorting, the window becomes -1, 1, 3. The median of this window is the middle element, which is 1. We append this value to our medians list, so medians is now 1. Next, as we slide the window forward, we remove the first element, 1, from the window and insert the next element in the array, -3, maintaining the sorted order. This updates the window to -3, -1, 3, and the new median, the middle element, is -1. We append -1 to medians, making it 1, -1. Finally, we slide the window forward again, repeating the process by removing the oldest element, adding the next, and recalculating the median. The medians list grows as the window slides across the array. Continuing with the sliding process, we remove the element 3 from the window. After locating its position in the sorted window, we remove it, leaving -3, -1. Then, we insert the new element, 5, into the window while maintaining sorted order, resulting in -3, -1, 5. The median remains the middle element, which is -1, and we append this to medians, making it 1, -1, -1. Repeating this process for the remaining elements in the array, we remove the oldest element, add the next, and calculate the median for each step. By the end of the sliding process, the final medians list is 1, -1, -1, 3, 5, 6. This illustrates how the sliding window operates dynamically, managing the removal and addition of elements efficiently while maintaining the sorted order required to compute the median. Now, let's explore a case where the window size, k, is even. With nums as 4, 2, 1, 3, 6, 5, and k equal to 4, we start by initializing the first window with the first four elements, 4, 2, 1, 3. After sorting, the window becomes 1, 2, 3, 4. Since k is even, the median is calculated as the average of the two middle elements. In this case, the average of 2 and 3 is 2.5. We append this value to medians, so medians is now 2.5. As we slide the window forward, we remove the oldest element, 4, and add the next element, 6, maintaining the sorted order. This updates the window to 1, 2, 3, 6. Again, the median is the average of the middle two elements, 2 and 3, which is 2.5. Appending this to medians results in 2.5, 2.5. With the final slide, we remove 2, add 5, and recalculate the median as the average of 3 and 5, which is 4.0. The complete medians list becomes 2.5, 2.5, 4.0. Finally, when the window size k is 1, the solution simplifies significantly. Since the window contains only one element at any given time, each element in the array is its own median. For example, with nums as 1, 2, 3, 4, 5, and k equal to 1, the medians are simply 1, 2, 3, 4, 5. This is because there's no need to sort or calculate averages. The single element in the window is directly added to the medians list at each step. The output for this case is straightforward and highlights how the problem reduces to a trivial case when k equals 1. The time complexity of our solution starts by analyzing the sliding window approach. First, we need to initialize the window by sorting the first k elements. Sorting these k elements requires O, k asterisk log, k, time. Once the initial window is prepared, we slide it across the array. Sliding involves several operations for each step. Removing an element from the sorted window takes O, k, since the list needs to be modified in place, requiring a shift of elements. Inserting a new element into the sorted list is more efficient, as it uses binary search with bisect.insert_left, making this step O, log, k. Finally, calculating the median is straightforward, as it just involves accessing the middle element or elements, which is an O1 operation. Together, these steps define the operations required for each iteration as the window slides across the array. Now, considering that the window slides over n k positions, where n is the length of the input array, each iteration involves O, k plus log, k, time. Adding this to the time required for initializing the window, the total time complexity becomes O, k asterisk log, k, for initialization plus any k multiplied by O, k plus log, k, for the sliding window updates. When we simplify this for large n and k, the dominant term is O, n asterisk k, which represents the overall time complexity of the solution. Shifting to space complexity, the sliding window itself is stored in a sorted list of size k. This requires O, k, space. Additionally, the medians for each window position are stored in an output list, which takes up to O, n, space in the worst case. Combined, this gives a total space complexity of O, k, for the window and O, n, for the output. For auxiliary space, there are no significant additional memory requirements beyond the window and medians lists. The helper function getMedian and other variables contribute negligible space usage. Thus, the total space complexity remains O, k, for the sliding window and O, n, for the output, leading to an overall space complexity of O, n. To compare, a brute force approach would involve recomputing the median for each window by sorting all k elements every time. Sorting each window costs O, k asterisk log, k, and with any k windows, the brute force time complexity is O, n k asterisk log, k, which simplifies to O, n asterisk k asterisk log, k. By leveraging the sorted property and efficient insertions and deletions, the optimized approach reduces the time complexity to O, n asterisk k, making it significantly faster than the brute force method. In summary, the optimized approach achieves O, n asterisk k, time complexity and O, n, space complexity, while the brute force method takes O, n asterisk k asterisk log, k, time and O, k, space. Looking at best, average, and worst case scenarios, the best case arises when k is small compared to n, meaning the time complexity is dominated by O, n. In the average case, sliding the window across the array involves O, k, operations for each step, resulting in O, n asterisk k. Even in the worst case, when k is large and close to n, the time complexity remains O, n asterisk k, because every window operation still depends linearly on k. Despite variations in input size, the space complexity consistently stays at O(n), as it is primarily determined by the size of the output list. When solving the sliding window median problem, there are several common mistakes to watch out for. First, using sorting for every window might seem straightforward, but it's inefficient. Sorting the entire window repeatedly leads to a time complexity of O(n*k*log k, which doesn't scale well for larger inputs. Instead, you should leverage dynamic data structures, such as heaps or balanced binary search trees, to maintain order efficiently. Next, it's easy to overlook edge cases, such as when the window size is 1, or when it equals the array size. Arrays with duplicate values or negative numbers can also introduce subtle bugs. Always validate these scenarios during implementation and testing. Another frequent mistake is mishandling median calculations for even-sized windows. Remember, in such cases, the median is the average of the two middle values, so failing to implement this correctly can lead to incorrect results. Lastly, inefficient deletion within the sliding window can be a bottleneck. Removing elements directly from a list or priority queue without the right structure can be slow. To address this, opt for data structures designed for optimized deletions, like balanced binary search trees or the two-heaps method. Another common pitfall is mixing up operations between min heaps and max heaps. For example, inserting elements into the wrong heap or failing to rebalance them properly can throw off the median calculation. To avoid this, follow the rules of heap balancing carefully, use a max heap for the left half of the window and a min heap for the right half, and ensure their sizes remain balanced. Shifting to some general interview strategies, it's crucial to recognize patterns in sliding window problems. These problems often require dynamic data structures, so think about how to add and remove elements efficiently as the window slides. While a brute force solution is inefficient, it's a good starting point to understand the problem and can earn partial credit in an interview. Once that's clear, discuss optimization strategies, like using heaps or balanced trees. This not only demonstrates problem-solving skills but also shows a systematic approach. Many candidates struggle with heap-based solutions, so practicing operations with min heaps and max heaps beforehand is highly recommended. Finally, don't forget to proactively address edge cases during interviews. Talk about scenarios like single-element windows, duplicate values, or arrays with large ranges to show a robust understanding of the problem. The sliding window median problem shares similarities with several other problems, and practicing these can deepen your understanding. For instance, in LeetCode 295, find median from datastream. The goal is to maintain a dynamic median using two heaps, a concept directly applicable here. Another related problem is LeetCode 239, sliding window maximum, which also relies on efficient data structures to manage the sliding window. Of course, LeetCode 480, the problem we're discussing, is a must-practice problem for mastering these techniques. Lastly, LeetCode 378, kth smallest element in a sorted matrix, involves using heap-based approaches to efficiently retrieve the median or kth smallest element. Each of these problems builds on the foundational skills required for sliding window median problems, making them excellent practice for interviews and real-world applications. There are several approaches to solving the sliding window median problem, each with its own trade-offs. The two heaps approach is one of the most efficient. Here, you maintain a max heap for the left half of the window and a min heap for the right half. The median can then be derived directly from the tops of these heaps. While this method runs in O(n*log k time, it requires careful implementation to ensure the heaps are balanced as elements are added and removed. Alternatively, a balanced binary search tree, like Java's treeset, can be used to keep the elements sorted within the current window. This method simplifies median calculation but may be slightly less performant than heaps in some cases, as it still operates in O(n*log k time. Lastly, there's the brute force approach, where you sort the window on every slide and compute the median. Although it's simple to implement, this approach is computationally expensive, with a time complexity of O(n*k*log k, and is generally unsuitable for larger inputs. Understanding these approaches and their trade-offs helps you choose the right solution based on the problem constraints. Thank you for joining me on this walkthrough of the sliding window median problem. We've summarized the key concepts, takeaways, and complexities involved. I hope this helped you better understand the problem and how to approach it. Don't forget to practice similar problems to solidify your learning. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!